Dr. S. Shankar is a professor, Department of Physics at Madras Institute of Technology, Anna University, Chennai. His area of specialization is solid-state physics. He has guided more than 10 PhD scholars. He has published more than 50 national and international research papers. He has 28 years of teaching experience.
Welcome to UGC lecture series in solid-state physics. Today's topic is on electrical properties of materials. Here the objectives are to understand the electron energy band formation in solids and effective mass of electrons in a given band and classification of solids into various categories like metals, semiconductors, insulators and so on based on the effective mass formulation, and electronic properties of semiconductors also we are going to study here. Then finally, we are going to brief about superconducting properties of solids. Now, how the energy bands are formed is outlined here in a solid. The solids are actually a collection of atoms either in a periodic manner or in a non-periodic or random manner. Here for an atom we have studied about the electronic structure and electronic energy levels, and this is schematically represented here in a Coulombic potential well. And when such atoms are brought together, then we have overlapping of potential which gives rise to quantum tunneling and overlapping of electronic energy levels or energy orbitals and giving rise to energy bands as schematically mentioned here. And this is also something about such formation of bands. So, this gives the schematic representation of one atom potential and the corresponding energy levels around a nucleus. Then if we bring two atoms together, then we have each energy level splitting up into two levels like this, and if four atoms come together, then we have each level splitting up into 4 levels like this, and if many atoms are brought together, then we have a continuous band. This is again another schematic diagram of how the energy bands are obtained as a result of potential overlapping. See, this gives rise to the potential overlapping and decrease of internuclear potential barrier, and this gives the schematic representation of potential variation along the line of atoms, and this gives the schematic representation of potential energy variation in between atoms. And the potential variation in between atoms can be represented as a sinusoidal function like this plus a constant. This is periodic over a distance say a, and conceptually we have this. So, from single atom discrete levels, discrete energy levels, to splitting up of levels into bands in a systematic manner like this. For 2 atoms we have 2 levels, for 3 atoms 3 levels for each discrete atomic electronic level, and then if many atoms interact, then we have for every single discrete electronic energy level in an atom a band arising. So, this is what the schematic representation of development of energy bands in a solid. So, this is the so called allowed energy band, and here we have a forbidden gap. This is the energy region between successive bands, and then so we have an allowed, then forbidden and allowed and so on. And as a function of distance, how the energy bands are varying. So, this is given here schematically. So, at a far off distance, the atoms are literally separate from each other and there is no potential overlapping, and hence the atomic or electronic energy levels in an atom are purely discrete. But when the distance is decreasing, then we have degeneracy splitting up into two levels. One level is decreasing in energy like this, and the other level is increasing in energy like this, and we have a separation. The orbital which gives rise to lowering of energy is actually responsible for the bonding of atoms, and the other orbital which gives rise to increase in energy is not favoring bonding, and so this is called antibonding orbital, and the energy levels are in between these two boundaries. And if large number of atoms are overlapping, then we have all the level splitting coming in between these two boundaries, and we have a continuous band. This is another schematic representation. See, at some particular distance A, we have discrete level spectrum at a far off distance A, and if we decrease the distance further, then after a point B, we have the energy level splitting up like this and overlapping, and here we have a continuous band from some region to this, and again if the distance is decreased further, then we have a band gap is opening up, and so this single band here splitting up into two and so on. How to understand these properties of electrons in this kind of potential variation? This is the so called periodic potential problem, and this was first studied by Chronic and Penny and very well known as Chronic Penny model. So, here we consider periodic potential in one dimension. So, every atomic potential is replaced by or assumed with a square well potential as a first approximation, and in between two square wells we have a barrier and so on. So, electron is moving across this series of barriers and potential wells. There is a theorem called Bloch's theorem, which gives information about the wave function of an electron which is traveling through this periodic potential array. Here after some lattice vector R, the wave function goes as a plane wave times psi k of small r, where this e power I k dot capital R refers to the periodicity after every r here, and small r of course is the distance or the position within the well or within one period of length, and in one dimension the same can be written as this psi of x equal to u of x and e power I k x, and u of x is the so called localized wave function within one well, and we have this property u small u k of r plus capital R is again periodic, and therefore, this is equivalent to u k of r. That means, the potential within one well is getting repeatedly occurring after every r, and this is to solve the Schrodinger equation with this periodic potential, and we have some boundary condition also for this, and we substitute E equal to h cross square k square by 2m, that is the kinetic energy part with the potential with the momentum equivalent to h cross into capital K, and u naught minus this energy is given this abbreviation. We solve this problem with all the boundary condition, that is psi of 0 is continuous and psi of a is continuous. These are all standard formulations, and if we solve simultaneous equations, 4 simultaneous equations which arise out of the boundary conditions, then we come across a matrix equation like this, and if we solve this, then we get an equation of this type, which is a combination of hyperbolic and sinusoidal functions like this. Then for simplicity, Chronic and Penny assumed further an assumption that if the width of the well is decreasing, then the height of the barrier is going to infinity, such that the product of u naught b is remaining constant, and hence this is factor is also constant, which is called as p here. Then there is a limiting case for this capital Q goes as capital K for QB far less than 1. This is a valid assumption. then in that case the above equation reduces to this sinusoidal kind of function, where we have one sine function, cos function, combination is equal to another cos function. And the above equation is rewritten for a given value of p equal to 3 pi by 2. So, we have some abbreviation, and finally, we plot this left hand side curve, and the right hand side curve of course has got two limiting values +1 and -1, because we have on the right side cos k a. So, the boundary values are +1 and -1. So, left hand side values which are well within this boundary values of right hand side only are allowed. So, this is a key point here, and this allowed region of left hand side values are shaded here with the color, and these allowed regions give rise to the corresponding energies which are actually plotted here, and the red line here refers to a free electron spectrum, whereas the quasi continuous lines represent the energy spectrum obtained from these allowed regions. Then this is again schematic representation of the same on both sides of the wave number, and here you can see that there is an important aspect, that at 0 wave number or wave vector, the energy is not 0 for particle traveling in periodic potential well case. And it is this reason why the electrons in a metal are at non-zero velocity always, even at absolute 0 Kelvin. And this way of representing E versus K is called energy band structure, or EK dispersion relation for electrons. And here for all k from 0 to plus infinity and minus infinity, for the entire range the curve is sketched over, but for all practical purposes the curve between minus pi by a to plus pi by a, this region alone is enough. And so, this is actually a repeated zone scheme of representing the same diagram, but for the next atom, if you work out a similar diagram, then that will fall on 2 pi by a plus b, keeping this point as the origin, and so a similar diagram will be plotted over here with this origin, and another diagram here, and similarly at 2 pi by a plus minus 2 pi by a plus by b, and so on. So, after every interval of 2 pi by a, the curve can be repeated, and finally that will look like this. This is called the repeated zone scheme, where the zone here refers to Brillouin zone or K region zone. And as I said, since the curve is repeatedly occurring, the part of the curve from minus pi by a to plus pi by a, which is periodic, alone is enough for all our considerations, and this parabolic curve is actually for free electron case, where the potential is actually 0 or simply constant everywhere. And as I said, the part of the curve from minus pi by a to plus pi by a alone is enough for most of our studies, and that is plotted here. This is called the reduced zone scheme. Here we can see about some dynamics of free electrons. Here from free electron energy band or energy structure like this, that is kinetic energy, where h cross k refers to the momentum. This is p square by 2 m for free electron, and k is permitted for the entire range from minus infinity to plus infinity, and so velocity is given by this formula d omega by dk, and so we have velocity equal to 1 by h cross d by dk, and that is also equal to p by m here. For Bloch electrons, the same thing is represented in a slightly different way. The wave functions are actually periodic wave functions like this, and one can construct localized wave function as a superposition of all such possible wave functions like this, where a k refers to the expansion coefficients and again the electron velocity is represented by the same kind of relation, and this is for 3 dimension. Del k comes here for 3 dimension, and for 1 dimension it is simply d by dk x. And effective mass formulation we are going to see now. In effective mass formulation, velocity is obtained like this, and time variation of velocity is the acceleration, and this can be calculated to get the force like this. And so, we can get if the mass quantity related to second derivative of energy with the k like this, and this mass quantity is not actually the rest mass of the particle, but it is a mass when the particle is in motion or driven by an external force, and this mass is actually different from the rest mass, because the mass represented here as m star is the effective mass. This is termed as effective mass or conceptual mass, and its variation is depicted over here like this. So, when the electron is at different points in the energy band, the velocity varies like this. You can see that if the band is empty, then electron may be thought of at the bottom, or there is no electron here. At this point, the velocity is 0, and if the electron is at the top of the band also, the velocity is 0, but somewhere in between it is maximum. In the same way, on the other side, it is negative maximum between zeros at the boundaries of the band, and you can see that the velocity is going from 0 to some negative and then approaching 0 and then to maximum and then 0, and this part will be repeatedly occurring for k variation. And so, when an electron is driven off by an external field and its momentum is increased, then its energy or the velocity will be periodically changing, and this sort of periodic variation is known as Bloch oscillation. And again effective mass formulation is here again, and m star is taken over and plotted here. So, you can see that the m star where the velocity is 0 is m star is infinity, plus infinity, minus infinity, and so on. And so, based on that we can categorize materials into various types like insulators and conductors. As I said, the point at which the velocity is maximum is somewhere at the around the middle of the band where the slope is maximum, and for all such materials where the electrons are filling up to this portion or so or around this region, the velocity is maximum, and therefore, the conductivity will be maximum. And at the bottom and top, that means when the band is empty and when the band is full, the velocity is 0. So, current density will be 0, and therefore, they will be behaving like insulators. And conductivity of course is given by n square tau by m, where tau is the relaxation time, which is the time interval between two successive collision on average. Then concept of a hole we have, see m star, if you take this m star is also going negative, particularly near the top of the bands. So, when a band is filled almost close to the top, then there the effective mass turns out to be negative, and so this is the region where the effective mass goes negative, and a negative effective mass electron is termed as hole. So, holes play a major role there, and then that is how the concept of hole came. And this is something about this, and your hole has a k vector as that of electron, but in the opposite way. So, when an electron is driven off along positive direction for a given field, then the hole will be driven off in the opposite direction, and so on. And this is something as a typical representation of energy band. This is for silver. This is the actual energy band, but what we have studied is all for one dimensional solid, which is very ideal. So, based on this kind of bands that we have seen, depending upon how the bands are filled, we have different categories of materials: metal, insulator, and semi metal also. So, this is a metal where one band is full and the next band is partially full, and here we have one band full, but another band having its minimum somewhere lesser than the maximum of this band at some other k point, this is also full, and this is the case of metal or a semi metal, but the conductivity here is lesser than this, whereas the other case is one lower band is full and the upper band is empty with large energy gap here, then this is the case of an insulator. So, this is something about the density of electrons or density of states for different categories of materials. Then we see something about semiconductors now. In semiconductors, actually we have a similar situation of an insulator, but when the energy gap is small, then for any thermal agitation, electrons from the top of lower valence band will go to the minimum of the next conduction band, and so both the bands will contribute for conduction, because this band is also partially full and the next band is also partially full, and here holes will contribute and here electrons will contribute, and so total conductivity will be due to electrons plus holes together. So, both the bands should be considered, and the energy gap here for semiconductors is of the order of thermal energy. In such case, density of electrons can be calculated or derived using a formulation like this. This is the general formulation used for calculation of electron density or particle concentration, and here Z of E is density of states, and this is the range of energy, and this gives the number of energy levels which are occupied with electrons within the energy range dE, and F of E is the probability that the electron is having its energy E. And here we have standard derivations for Z of E dE, and it is proportional to e power half, and this is substituted there. And one more thing about the semiconductors is that energy of electrons is commencing from conduction band minimum, and so there is a common shift of energy by E c and use that. And if you use a thing along with this probability for the electron to occupy a given energy E, then we get the electron concentration calculation going somewhat like this, and finally we have this expression for electron concentration, and E f is a Fermi energy and E c is the bottom of conduction band, and so it is the difference between the two energies coming into this expression apart from a constant factor here. Similarly, for holes we can work out, but for holes we have to consider valence band top, and the energy of holes is conceptually going downwards, and probability for the occurrence of a hole is missing probability for an electron in a given level. So, that is given by 1 minus f of E. This f of E is for electrons, and so we substitute all that, and once again proceed with similar derivation, then finally we get expression like this for hole concentration. And here is one important thing, that the product of electron hole concentration will be equivalent to this intrinsic carrier density square, and then this can be shown to be valid. This relationship is called as a law of mass action in semiconductors, and this is about intrinsic semiconductor, where the Fermi energy is exactly at the center of the energy gap from between valence band and conduction band. From the above equations we can work out a relation for the Fermi energy as a function of temperature, and this is a linear variation, whereas this quantity is a constant which refers to the central position here, and in addition to this we have temperature factor, and so at absolute 0 Kelvin this factor goes 0 and we have this factor, and so Fermi energy is exactly lying at the center of the gap. Then for extrinsic semiconductor we have two types, p type and n type. One for n type, pentavalent atoms are doped in a given semiconductor, and we have excess electrons, and for p type trivalent atoms are doped to get lack of an electron giving rise to p type, and so on. And in such case we can work out the Fermi energy, and then there is one donor level for n type, and this donor level is very close to the conduction band, and for such case we can work out the carrier concentration like this, and also the Fermi energy, and the Fermi energy is varying linearly, but also the temperature is appearing in the logarithmic argument. Carrier concentration works out to be like this. Here we get the energy difference between the donor energy and the conduction band minimum energy coming into the picture, and so variation of Fermi level with the temperature is outlined here. Actually, at high enough temperatures, the Fermi level coincides with the intrinsic case, whereas at sufficiently low temperatures, the Fermi level is in between this ED and EC. Then as temperature goes off, then the Fermi energy comes down ED and coincides with the intrinsic case and becomes exactly EC plus EV by 2. And for p type semiconductors, a similar thing. Here EV minus E acceptor, that is the only difference, otherwise here MH is coming, and similar behavior is there with respect to the Fermi energy in between valence band top, that is EV, and acceptor energy. The Fermi energy will be lying there. Then here is one important categorization of semiconductors: direct band gap and indirect band gap. This is very important actually, because the conduction band minimum and valence band top both do not occur in EK relationship at the same value. And here we can see that for this conduction band, the energy minimum is here, and for valence band the energy maximum is at the same K point in the E versus K relation. This is called direct gap, because the energy gap is defined as the energy difference between valence band top and conduction band minimum. And these 2 points do not occur at the same K value here in certain materials. Here also energy gap is formed, but between the energies of different K values, and this is called indirect energy gap formation, and there are drawbacks for this, and normally elemental semiconductors have this type of energy band structure which are not suitable for direct transitions, which are preferred in optoelectronic purposes. Then Hall effect. See, Hall effect is actually experiment performed by Hall by taking a rectangular slab of a semiconductor and subjecting it to some magnetic field and applying a perpendicular direction electric current. So, current is flowing here and magnetic field is applied like this. Then he happened to observe along a perpendicular direction to both B and I, one voltage developed along this Z direction, and this is a strange phenomenon. This was called as Hall voltage later on. This is for N type, and there is one theory for studying this phenomenon, and theory gives an expression for Hall field, that is Hall voltage and the corresponding Hall electric field, and the relationship is obtained as EH equal to RH, or a constant of proportionality, multiplying J into B, where J is a current flowing and B is a magnetic flux applied, and so this constant of proportionality is finally obtained like this. And we have an explicit expression for RH. So, since all these quantities are experimentally measurable, one can obtain RH. The significance of RH is that it is positive type of charge carriers and negative for negative type of charge carriers. This is very important thing. And further, this RH being equivalent to 1 by Ne, E is the electronic charge magnitude and the charge nature comes over here. So, if E is for holes, it will be positive here, and if E is for electrons, it will be negative here, otherwise the magnitude is same. So, if you can work out RH from these measurements, then this N can be obtained. It is a very important application of Hall effect, that is carrier concentration and type of concentration can be studied. Now, we have come to the end of this lengthy talk here, and we have summary. So, here we summarize that the electronic energy bands are studied fundamentally, and effective mass formulation is also studied, and the concept of holes and their dynamics is also studied. Then general electronic properties of semiconductors and Hall effect are also studied, and we have a few questions here, like how energy bands are formed, what is Fermi energy, and how does the Fermi energy of a p-type semiconductor vary with temperature, what is Hall effect, and what are the uses of Hall effect. So, thank you.